Okay, let's talk about a parabolic radon transform for multiple attenuations. Multiple attenuation, so far we have learned a number of methods. We learned FK transform for multiple attenuation. We try to have an NMO correction. For primaries, we use the velocity slightly lower than the true velocity because we do the overcorrection of primaries, but under correction for multiples. So that means after FK transform, the multiples and the primaries are in the positive negative domain, positive K, negative K, right? They're separated by the direction. The tau P transform, we already learned that for multiple attenuation. And in the tau P domain, the multiples becomes periodic because for any multiples, they actually travel in the same P value, right? Constant Rayleigh parameter, sine theta over V, that's constant. Right, so for same P trace, the multiples become periodic. So that means we can use a predictive deconvolution to do the multiple removal, right? However, this predictive decon in the tau P domain only applicable to the 1D Earth model, right? Observed structure should be in 1D. And we also know that stacking can somehow cancel multiples. But the issue with stacking is for zero offset or near zero offset traces, because the curve gradually becomes flat and then move out at near offset very small, so the multiples cannot cancel each other. But in the practice, we learned that one powerful but brute technology is inner mute, right? After NMO, we do inner mute. We mute near offset traces before we do a stack, right? So we already learned this method for the multiple removal. All these three based on the velocities, right? In the FKT multiple, let me just review what we learned. In the FK domain, actually, before we do FK transform, we try to overcorrect the primaries. So that means the primary will have a negative K, and the undercorrected multiples, just of course, because your velocity is much higher than the multiples, right? Although the velocity is lower than the true velocity of a primary, but it is still positive. So you have a negative K for the primary and a positive K for the P. So and then you can separate them, right? So after FK transform, you simply mute them in the FK domain. And then after that, because this NMO is not the ideal NMO, you need to remove this NMO and so recover to the original time offset function, original time offset curve. That's the cartoon we showed before. You know, in the ideal situation, after NMO, your primaries becomes flat. So that means you can stack them together, right? And in the stacking, actually multiples, because multiples have a move out difference, so you can somehow cancel the energy of the multiples. However, for the near offset, because the curve towards the apex, towards the point here, that's almost flat. So this bit becomes the multiples remain. So what do? Usually you do the after NMO, you do the inner mute, and then you do stack, right? That's the NMO. But for the FKD multiple, we do overcorrection for the promise instead of flat, but it becomes a negative dip, and the multiple still positive dip, and then you do Fourier two-dimensional Fourier transform, right? Promise and multiples. Promise negative dip, and the multiples positive dip. We saw this slides before. This CMP gather, raw CMP gather. You can see the after NMO, you can see this one become flattened, right? That's the normal NMO. However, you want to do the D multiple, you want to remove multiple, you use 90% velocity. 90% of NMO velocity, you have overcorrected multiple promise, the multiple still distraction, and then you do the FK filter. FK filter includes FK transform, filter, and inverse FK transform, right? You end up this result, but this result is an NMO, and then just an NMO with 90% of true velocity, and then you remove that effect, you end up the normal move out without an NMO effect. That's right. So multiples for long period multiples, which is predictable, right? And in the CMP gather, they have a different offset, right? So all this we call the velocity fields, right? In the FK, we use 90% velocity, so we can have a negative positive P, negative positive dip. That's based on the velocity, right? Based on the velocity. So this everything so far, FK, tau P, all based on the velocity, right? And stacking also, NMO also. So velocity is a key element here. So that's all this we can call the velocity field. But move out is hyperbolic, not a linear. That's one thing, right? In the tau P domain, tau P is a linear stack, but actually it's hyperbolic is not linear. Okay, so whether this hyperbolic can be used to separate primary multiples, that's the one we will discuss. After NMO, this hyperbolic becomes parabolic. That's the name parabolic random transform came from. Right, after multiple, okay, that's the premise, and the multiples, they're all, the rated curves are multiples. Premise, or the blue curves, they are quite close to each other, right? And after NMO, that's premise becomes flat, and the multiples, this curve, mathematically, you can prove that it's more likely, it was hyperbolic, but now, after NMO, this becomes parabolic, right? Parabolic. And I will show you what parabolic really means, okay? So basically, it's just parabolic. Based on this curvature, and we use called parabolic radon. Rather some are along the straight line, but no some are along the parabolic curve. Hyperbolic parabolic alliance. Let's distinguish that. So primaries and the multiples in CMP together are hyperbolic. That's based on the so-called Dix equation, right? Based on IMS assumption. For layered structure, for the small offset, we can assume IMS velocity equal to the NMO velocity, right? That's assumption. So that's basically approximation for hyperbolic. The hyperbolic transform, we can do hyperbolic transform because we have squared everywhere. That's will be very expensive. We don't know how to do squared variable Fourier transform, right? We can do the X transform, T transform, Fourier transform, very easy. Oh, okay. Efficiency is due to the use of fast Fourier transform, right? If we can do the Fourier transform with respect to T, we can do the fast Fourier transform. If we can do the Fourier transform with respect to the X, we can do the fast Fourier transform, right? That's efficiency. But the hyperbolic curve, if we remember, hyperbolic equation have a T squared. We don't know how to do the T squared Fourier transform, right? And another term is X squared. So we don't know how to do X squared Fourier transform. See that? So after NMO, that's T squared becomes T. X squared becomes X. You can now use a Fourier transform. That's the trick here. Okay. So parabolic, after the Fourier transform, after the NMO, this hyperbolic curve becomes parabolic. Because parabolic have a T power 1, X power 1, so it's you can use a fast Fourier transform. That means very, very cheap, relatively. Okay. Of course, you need to do the Fourier transform. Okay. So fast Fourier transform is a key role here. Okay. After NMO, hyperbolic curves becomes parabolic curve. That's the key. The parabolic formula is this. You remember, hyperbolic curve is T squared equal to T naught squared plus something X squared divided by V, right? Divided by V squared, sorry, X squared divided by V squared. But here, after the NMO, it becomes T equal to T naught plus X squared, and Q here. Q is not exactly 1 over V squared, because you already do the NMO, right? But this one, we simply call the curvature, because X squared, we call the curvature. So parabolic transform, we just simply call the curvature. Tau P transform, we use tau with the interception time, right? And the P is dipping angle. But here, it's also tau. Tau is the interception time, which is T naught. And the Q is curvature. So tau P becomes tau Q. Let me repeat it. Tau P is a dipping. Here, tau Q is the curvature of this parabolic curve. Okay. And because this in the Fourier transform domain, easy to implement Fourier transform domain, we can use the least square method to do a frequency by frequency fitting to get a perfect result, right? So you can see the logic here. In the seismic community, we call this parabolic radon simply called the radon transform. Okay. In the other field, the tau P transform is called the radon transform. But in seismic community, we call the parabolic radon as a radon transform to somehow distinction from the linear radon, which means tau P transform. Let's show you how to implement. We know this time X domain data, right? For this one, the curvature is 0, right? So curvature 0, and the tau here is here. The vertical axis interception time is tau. You have a dot here, and here you have also another one. So after NMO, your prime is actually energy concentrated around Q equals 0 because it's almost flat. The curvature is 0. Curvature means 1 over the radius of a curve, right? Because the flat one means the radius infinity. 1 over that is 0. Okay. And then if you use a different Q, different curvature, like Q1 here, you can see that. Okay, this one just have a something that I only here, you see it? And then the Q2, right, this one have a strong energy put here. Tau again is in the intersection time. Q is curvature, constant curvature, but only along this curve you have energy, right? Q3, you can see this one have perfect match. That's the tau p. Not sorry, that's the parabolic radon transform. Input is a xt after the parabolic radon. When q equals 0, here, basically, those are the parameters, right? And all those must be the multiples, right? So you can see after the multiple removal, you simply cut off this part and then do the inverse. You end up parameters here, right? And the difference between this and the output, you can see here, right? You together the multiple, together with this multiple, this multiple, this multiple, but you also lost some parameters, right? Why is that? Because this one is the energy is not focused here. You have a spread energy spread all different P, all different Q, right? If we mute from here, that means you have a primary energy mute out, right? You of course you have a good perfect, you have a good primary keep it, but also have a energy loss. Now, because energy is not focused, why is that? Again, it is because of the limited aperture, right? In the X space, ideally should from negative infinity to positive infinity, but it's not. Right. So what do? We use the least square manner, least square fashion, this square method to do the fitting, to try to minimize, okay? So use the least square to optimize multiple model. And then the multiple then can be removed or subtract. So how we do that? Right, that's the original data in the TX domain. Okay, I repeated many times. I said you should distinguish the data space and the model space, right? So the original data we call it data space. After transform, either here, radon transform, we call the model space. So any sample here is a model space, right? That's the model space. So data space to model space, this transform is subject to a transform operator, right? So D multiplied by operator equal to model, yeah? So that means, and then you do the inverse transform, you based on the model space, which is M here, model space data, pre-multiply by inverse operator, you generate the final result, reconstruction here, right? That's you have just forward the inverse. That's the formula here. Data space, model space, and then from model space back to the data space. So modeling equation is D equal to arrow M. Arrow is inverse transform operator. So arrow basically is inverse of G, but G is not squared, not generally can you do not have a general sort of inverse. You do need something called a generalized inverse, right? So for this one, if we pre-multiply left hand and right hand side, pre-multiply by arrow transpose, I put H here because arrow here is a complex number. Arrow transpose means the Hamilton transpose means complex conjugate transpose. Okay, so you pre-multiply RH here, pre-multiply RH. You have a RH D equal to RH arrow M, right? And then this RH arrow is a squared matrix. Now you can do inverse. So RH squared, this is a squared, you can do inverse. So both sides multiply by inverse of that. On the right hand side, they end up only M. On the left hand side was arrow HD, but no pre-multiply arrow H arrow and the inverse. See that? So that's the final result. What's this? This is exactly the solution of a least square solution, right? I did imagine that if you have an interest, you go to see my textbook for subsequent motion. I spent a number of chapters talking about this. Okay, so that's least square. So arrow for the arrow only depends on the geometry. Does not depend on the data. Only depends on the source receiver interval and the time interval, right? Offset interval. So it only depends on geometry. Okay, so this is the formula. That's the least square. But sometimes this least square is not stable. It's not stable because this inverse here, 1 over something next to 0, numerically will be unstable, right? So what we do when we're talking about stabilized inverse least square, we add in something to the main diagonal, which is pre-whitening, if you remember, because H arrow here is autocorrelation. The random noise autocorrelation is a constant, so you're adding something to main diagonal. In this case, actually we try to something called white noise adding here to the main diagonal. This will stabilize the inverse operator. Okay. And then furthermore, we are just try to change the arrow into something else. That will be next step of the least square. Let's talk about least square now at the moment. So how do we implement that? First of all, we do transform to frequency domain. That's very fast because for each individual trace, you just implement the FFT. And then in the frequency domain, for each frequency, you calculate the matrix error. Matrix error only depends on geometry, but also, of course, depends on frequency, okay? So frequency dependent, geometry dependent. And then you try to get at least square inverse of the squared matrix. If not good enough, you just add in something to the main diagonal to have a stabilized solution. The inverse calculation is quite straightforward. Sometimes use a SVD called singular variable decomposition. Sometimes use a LU decomposition or other method, iterative way to do that. That's the numerical tools. I do not spend time here, right? And then you do the transform back to time. That's the least square implementation. Let's show you example. If you remember this diagram, that's the simple parabolic radon. Just a straightforward radon transform from data space to the model space, from TX space to the tau Q space, right? And I said the energy here is not focused on this point, but spread out. And after the mute, is some part of it. Primary energy actually also being muted, right? So that means you have a significant difference or significant residuals. Now, if we use the least square, this energy here disappear, actually focus, much focused to here, much focused to here. If I compare the two, what do you see here? Try to see the red pattern here. Okay, red pattern, extend to here, quite a wide range in terms in the Q, right? And for example, here, this one quite a wide range to here, but they use this squared, you can see narrow, right? Much narrower. So energy much more focused. This thanks to this square. This square means it's not a regular transform, but minimize the residual. Then you compare the difference between the input-output, which is here, right? This one much weaker than the previous one, but still you have something here, right? We will do next step. So you get to look at the multiple, right? But also something wrong here, because this one, in the next to the zero offset, you see the energy here, the multiple is not removed, right? Because you only remove the far offset, but the near offset still here. So this it's get improved, but not really the best one we want. What do we do? And then remember, I put a little lambda here as a stabilization factor for this square solution. And now we use this called sparse, instead of constant, but we use the variable here. This one, we implement it iteratively. First of all, we get M. M is vector for individual point. And then you based on the individual point, you find out the solution, the maximum solution, as inverse of that. This is called a sparseness constraint. If you see the inverse theory, sparseness constraint, which means in this square formula, you not only have a data fitting, which means we call the this square, right? We try to have a minimal residual, which means data fitting. The data output fit to the data input, have a minimal residual. But here we're adding another thing called a model constraint. Model constraint. We try to see the model constraint and the model output try to close to this one, to M1, M2, M3. That's called a sparseness constraint. So in the inversion theory, we have two terms instead of single term data fitting, but now have a data fitting plus a model constraint. These two together, the result will be this. So this one is instead of a constant lambda, now becomes a diagonal matrix, and the individual elements varies with the previous solution, right? And sometimes in your software, that's simply called a high resolution. High resolution really means called spark. Sparkness, right? And in terms of inversion theory, it's called a sparseness constraint. Sparseness constraint. So let me summarize how to implement high resolution random transform. First of all, this is a constraintless square solution. So this square, which means data fitting, but now have a model constraint. Okay, and this inversion, this square is inversion, but because of sparseness constraint, the parameter actually due to the previous step. So this is a nonlinear iterative solution. It's not a one go, it's an iterative. Okay, you have a initial solution and then use this as constraint to the next step. And then so on and so forth. Okay, so it's an iterative, nonlinear solution. Because the first iteration already gets some solution very close to final solution, and within the vicinity of final solution, you can assume the problem becomes linear, and then you can do iteration. Okay, that's a linear iteration. This will we'll see examples largely improves the quality of multiple attenuation. For example, here, that's the standard is a square. You see that the red curve here disappeared, red spread, the energy focused to here, but it's not really completely focused, right? So still have some spread. Here, some spread, right? It's not exactly Q equals 0, or not exactly Q equal to this one, the curve. So what we do, we try to narrow that, try to make this spread further narrowed. Okay? And that is the constraint. You try to, for this Q, you try to squash the energy into the single point, right? Squash to the single point. Okay, so that's you can see the red curve here. Only that short period, and here short period. But this steroid, it's just called concentrated square. Let's see the result. That's the input after an MO, of course. Only after an MO, your hyperbolic curve becomes parabolic, right? And then you can use parabolic radar. So that's after an MO. And the output, you can see all becomes flat here. And all this multiples gone. And you can see the difference. Those are the multiples. Even for the near offset, multiples also removed. So let's compare the radon demultiple and the FK demultiple. First of all, radon uses a parabolic, which means after an MO, the multiple curve from hyperbolic becomes parabolic curves. Okay. Especially at a near offset. You see that FK has a trouble with near offset. What we did, we use the inner mute, right? And the other methods, they also have a tau P transform. We also have trouble with the inner mute, with the near offset, right? But this one, we have a perfect match. So that means typical of a near offset, we can get rid of multiple, right? Of course, radon transform is much more expensive than FK. FK just straightforward, fast Fourier transform twice. But for the radon transform, we basically for each individual frequency, we need to do that least square solution iteratively. Right? If we only do the single step, that's a standard least square, but you need iteratively to generate a high resolution radon. So it's much more expensive, right? However, this is more flexible. You can fit the curve. Even there's some dipping water flow, you still can somehow always find a curvature fit to that curve, fit to that point, right? So that's quite flexible for the subsurface. No longer rely on a 1D assumption. This thing is very important. Radon, in this case, better preserve the amplitude. As we said, amplitude variation versus offset is a very, very important information for the later stage reservoir prediction. Okay, so this one's better for this purposes. Okay, and of course the results have a highly improved quality. Okay, let's summarize what we learned today. This session we mainly focus on the coherent noise, typically focus on the subsurface multiples, right? But the coherent noise also includes like a direct wave. We're talking about how to effectively separate direct wave from the subsurface reflection. This is a tau p transform. Because tau p transform, p is a straight line, it's linear field, right? It's a linear assumption. So that means direct wave can easily to be summed into a single point in the tau p domain. So tau p transform is the proper way to get rid of a linear coherent noise. That's the one. Okay. Otherwise, you ask me why you don't we straightforward go to the last one, right? Why we do need tau p? If you remember when we're talking about predictive decon, we use a tau p transform and then we mute both sides, which means we get rid of direct waves. So all this is actually useful, but with step by step. So for the coherent noise, typically for direct waves, we use a tau p to get rid of the direct waves, straight lines. And then the rest part, we use a predictive decon. We use a predictive decon to get rid of multiples. Okay, that's very good because this predictive decon in the tau p domain is much better than the predictive decon in the TX domain. Because in the TX domain, the assumption of periodical multiples, the assumption is not satisfied for far offset. But in the tau p domain, p is constant along the ray path, and this is satisfied. Okay. However, for this one, for the tau p domain deconvolution, there's a very, very important assumption, which is the subsurface model is a 1D model. It's a 1D model, right? If you have a dipping structure, particular decon will not work. That's the 1D model, right? But it's very hard to get a 1D model now, and then we move on parabolic random transform. Parabolic random transform. Parabolic random transform means you after NMO correction, your premise becomes flat. And the multiples becomes parabolic curves. Multiples become parabolic curves, right? After the parabolic random transform, which is which is a curvature for the premise curvature is 0. So all the premise energy will be focused onto the central point next to Q equal to 0. And the multiples actually is non-zero for Q. The one important problem of this, because the data set we only have a limited aperture. So it's not ideal integration from negative infinity to positive infinity. We have limited aperture. So that means we do need somehow, instead of a straightforward transform, we use this square transform. So we turn the forward problem, which is M equal to GD forward transform from data space to the model space, into an inverse problem. The inverse problem means we set up from a data space back to the model, from a model space back to the data space. Okay, and then we use the inverse operator to generate. So let's recall that. Let's review that. One is called from a data space to the model space, from TX space to the tau Q space. That's called a forward calculation, right? You can simply write equation like M equal to G multiplied by D. So D pre-multiplied by G, right? That's M equal to GD. That's the forward. But the problem with this is that is not infinity, that aperture, right? It's not infinity, have a limited space. So what we do, we turn the equation around. We use D equal to Lm. D equal to Lm. And then we solve from this equation, from this system of linear equation, we solve M. So M will be the general inverse of L multiplied by D, right? And the general inverse, we use a mathematical formula called least square. Least square, which means we minimize the particular data, which is D, to the original data. That's called least square. Because of this square, we will try to get rid of the edge factor, get rid of the aperture limitation, right? That's the least square. And in the least square, we use stabilization factor, but we also use something called sparseness constraints. Sparseness constraints is a capital lambda, which is a diagonal matrix. But each element in the main diagonal variable depends on the previous step result. It's not constant. If it's constant, it's stabilized least square. It's not sparse, but it's variable with the previous step. So it's iteratively improve the sparseness. That's end up we call the high resolution Breton transform. The good thing is this one can easily get rid of all the multiples, even for the new offset multiples. Right, that's one, A. B, this transform actually have a good fidelity of AVU information, amplitude variation versus offset. This information is very important for next step reservoir prediction. Right, so we try to do the best job for this. So from up to this point, this data will be ready for next step reservoir characterization and geological interpretation. So this is the random noise removal. Oh, no, sorry, the coherent noise removal section here.